Okay, thank you very much. Yes, first of all, I thank the organizer for invitation. So I'm very much delighted to be here. And of course, I spent 3 years and a couple months at IPMU, and that time was kind of treasure for me. And today I will speak about axons. Well, actually, I just put the axons without thinking about it very seriously. But anyway, first of all, I will give a review of axons to those who are not familiar with this topic. Then I will talk about a couple of my recent crazy ideas. And so there are many experiments they're ongoing and planned, many experiments searching for axons. And the original motivation of the axion, I mean the QCD axion, comes from the strong CP problem. Namely, a priori there's no special reason to drop the so-called theta term shown here, which violates P parity and CP because both are not a symmetry of nature. Then we naively expect the coefficient of this parameter to be over the unity, which, however, is very strictly constrained by experiments. Theta must be less than about 10 to minus 10, and why it is so small is a strong CP problem. And one possible solution is a Petrarch mechanism, which effectively replaces the constant theta parameter with a dynamical field axion denoted by A. Fa is the axion decay constant. And this axion makes the theta parameter dynamical, and axion acquires potential during QCD field transition due to the QCD instant effects, and it is stabilized in such a way that it cancels the theta parameter, so that effective theta parameter becomes 0. And that's solving the strong CP problem. And because potential height is set by the QCD scale, the typical curvature of the potential or the mass of the axion becomes smaller when the periodicity, namely the decay constant, becomes larger. And they satisfy this relation. And recently, the axion-like particles, which have properties similar to the QCD axion, have been also studied extensively in the literature. And they do not necessarily satisfy this relation because their masses are considered to have different origin. So usually their mass and decay constants are treated as independent free parameters. And this dynamical solution of the strong CP problem works wherever the axion initially is. So we expect the initial position of the axion is generically deviated from the CP conserving minimum by a factor of order unity. So it starts to oscillate about the CP conserving minimum here with an amplitude of order Fa. And then you can explain the observed dark matter abundance if the decay constant is around 10 to 11th or 12th GeV. And for such large Fa, the axion mass is very small, so it is stable on the cosmological time scale. So axion is a very interesting dark matter candidate because it's originally motivated by the solution to the strong CP problem, which has nothing to do with dark matter. But it comes out such dark matter candidate kind of automatically. And axions have various couplings to the standard model field. And one is the coupling to gluons, shown here. And this is defining property of the QCD axion. And axion is just pseudo-scalar field. So you don't have to couple axion to gluons. One needs colored fermions, quarks, running in the loop. And if unknown heavy quarks run in the loop, such an axion model is called hadronic or case-freeze axion. And if ordinary standard model quarks run in the loop, it's called the DFSZ axion model. Of course, if you like, you can combine these and both heavy unknown quarks and standard model quarks, or some of the standard model quarks run in the loop. And anyway, the coefficient of axion coupled to gluons, NDW, depends on the number of quarks and their charges under the 1PQ symmetry. And this domain one number, NDW, is very important when you study the topological defects associated with spontaneous breakdown of 1PQ symmetry, because this determines the structure of the cosmic strings and the domain walls generated around the cosmic strings. And similarly, axions are also coupled to photons. And it is customary to parameterize the coupling of the axion to photons in terms of GA gamma gamma shown here, and which is inversely proportional to FA. And in contrast to the coupling to gluons, this coupling to photons does not generate the axion mass unless they are magnetic monopoles. And also axion is coupled to fermions, like electrons or nucleons, but coupling to electrons is more model dependent. It can be suppressed in the hadronic axion model. And there are many experiments and, and observations which try to detect axion through these couplings to the standard model field. And they can be broadly classified like this according to the production mechanism and the detection methods. And the production mechanism of the axion can be broadly classified in terrestrial production and the celestial production, so produced inside stars, and cosmological production, so like the misalignment production mechanism I mentioned before. And the detection method can be either direct or indirect. So due to limited time, I cannot explain all of this, but for instance, if you take the terrestrial production and direct detection, and one of the experiments in this category is so-called light shining through the wall experiment. This is a very fancy experiment. So you apply the laser at the wall, and you apply the magnetic field. Then some of the photons are converted to axions, and because axion is coupled, very weakly coupled to ordinary matter, so the axion just pass through the wall. And on the other side of the wall, you apply magnetic field again, the axion is converted back to photons. And this type of experiment try to find those converted photons. Alternatively, you can also look for the effect of axion emission on the photon polarization, like PV-LAS experiment. So the typical example of LSTW experiment is ALPS or ALPS-2 at DAISY. And the indirect method is, for instance, axion is coupled to spin of fermions that would induce spin-dependent fifth force between polarized matters or polarized matter and bulk matter if CP is broken. And it has been searched for by many experiments, but future experiments called Ariadne can improve the existing bounds by many orders of magnitude. And this, one example of celestial production is the solar axion. The axion, if it exists, can be produced inside the sun copiously. And the CAST experiment or the future IAGSO or TASTE, these solar axion such experiments try to convert axions coming from the sun to the X-rays. So this IAGSO is a future axion search experiment, probably hosted at DAISY. And TASTE is a recently proposed Russian experiment whose projected sensitivity is comparable to the baby IAGSO, the first version of IAGSO. And also the axion could affect the star cooling, and it could affect the lifetime of stars in the various stage. And if axion exists at dark matter, they can be searched for by many techniques. And so as you can see from this, the color of this letter, actually the green ones means that the experiments make use of the axion coupled photons. So as you can see, so many experiments are targeting at the axion coupled photons. And this is the current constraint on the axion coupled photons. X-axis is the axion mass ranging from 10 to minus 8 electron volt up to 10 electron volt. Y-axis is the GA gamma gamma ranging from 10 to minus 16 up to 10 to minus 8. And this gray region is already excluded by CAST experiment. The latest bound is slightly better than this, about 0.66 times 10 to minus 11 GeV inverse, which is comparable to the Stark-Cooling argument constraint horizontal branch star. And the bound will be improved by about 1 order magnitude by IAGSO, a future axion search experiment. And this yellow bound corresponds to the preferred range of the QCD axion. And some of the parameters have been already excluded by ADMX, and many other experiments are planned to search for the axions at different masses. Now, the time for crazy ideas. And recently, with my graduate students and the postdoc, we proposed a scenario we call it miracle, which prefers this particular parameter space, which is just around the current bound or slightly below the current bound. So it will be probed or checked very soon by the future experiments. So what is this? So the idea is based on the unifying the inflaton and dark matter. As everybody knows, inflaton drives inflation in the very early universe, and the dark matter played very essential role in structure formation. And usually inflaton and dark matter are considered as a different object, but actually they have something in common. So both are electroneutral, and they both occupy a significant fraction of the universe, okay? Of course, at different times. And usually after the reheating, namely the inflaton decays into the standard model of fields, then usually this reheating process is assumed to be complete. Namely, the inflaton just disappears from the universe after the reheating. But if for some reason the reheating is incomplete, even though most of the initial energy of the inflaton goes to radiation, some small fraction of them could remain, and later on it may become dark matter. And such an unification of inflaton and dark matter due to the incomplete reheating has been occasionally studied by some people, but the most non-trivial constraint on such an or requirement on this scenario is how to stabilize the inflaton interpreted universe. And in most cases, people simply assume Z2 symmetry on the inflaton, but in our scenario, we tried to unify inflaton and dark matter by a single axion-like particle, and the longevity of a dark matter particle is simply due to its light mass. And so by axion or axion-like particle, I mean it has periodic potential, so it enjoys discrete shift symmetry, and any periodic potential can be given as a Fourier series, so it is given by the sum of many cosine functions. And if one of the cosine functions dominates the potential, such an inflation model is called natural inflation. Like this, so capital lambda parameterizes the potential height, and F is the decay constant, so it's parameterized periodicity. And it is known that with single cosine function, you can only have large field inflation, namely the inflaton excursion exceeds Planck mass during the last 50 or 60 efforts. And so for this, the decay constant F must be greater than about 5 times the Planck mass in order to be consistent with CMB observations. And there are a couple of arguments whether or not such a large super Planckian decay constant can be derived from the UV theory, like string theory. But even if this is somehow justified, the predicted values of NS and R, the properties of density perturbation, are not favored by the current observation. So in order to have successful inflation with, say, sub-Planckian decay constant, you need at least 2 cosine functions. And because with 2 cosine functions, it is in principle possible that these two can conspire to make the potential very flat over such a field range around the top of the potential. Then inflation can happen. And that's called axion hilltop inflation. So with 2 cosine terms, and for certain parameters, so for certain values of relative phase and relative height, you can make the potential very flat around the top of the potential like this. And so it is approximately given by the constant terms minus some quartic terms. So quartic hilltop inflation is possible with 2 cosine terms. And what is interesting here is that if you take n as an odd integer, the potential is also flat around potential minimum. This is not the case if n is an integer, even integer, but if n is odd integer, then you have upside down symmetry, so the inflaton is both light around the top of the potential. This is required for inflation, and which implies that potential is also light at the potential minimum. So in this case, the flatness of the potential required by successful inflation implies the very light inflaton mass at potential minimum, so it can be very long-lived. So longevity of dark matter particle in this case is just direct consequence of slow roll inflation. And we can use 2 observational inputs in order to derive the relation between decay constant and mass. So first of all, the CMB normalization fixes this ratio, potential height, and the decay constant, okay, the periodicity of the potential, to be 10 to the minus 12. And the Friedmann equation relates the potential height to the Hubble parameter during inflation. And in order to explain the observed scalar, spectral scalar index, which is slightly smaller than unity, and because the deviation of the spectral index from unity is simply given by the ratio of the curvature of potential to the Hubble parameter, the inflaton mass should be over the 10% of the Hubble parameter during inflation. So you can eliminate capital lambda and Hubble parameter from the three equations, and you get this relation. And in contrast to the QCD axion, the mass of the inflaton increases as the decay constant. Okay? This is not the case in the case of QCD axion. And for successful inflation and successful reheating, we need to couple somehow this inflaton to the standard model particle. And we introduce coupling to photons like this. Then this is C gamma is model dependent parameter, but generically it's over the unity or over the 0.1. So, but by the way, this is the inflaton mass or ARP mass, and the y-axis is coupling to photons. And this is Casband, horizontal branch star, and this red lines are the region preferred by this ARP inflation model. So this region is required by successful inflation based on the ARP inflation model. And after inflation, the inflaton decays through the coupling to photons. Okay? The first it decays into a pair of photons, and after it gets thermalized, the photons acquire the thermal mass, then simple particle decay stops, but instead this whole dissipation process becomes important. And this dissipation rate actually depends on the temperature, which decreases faster than Hubble parameter. So at a certain point, the dissipation effect stops. And we are left with some amount of the inflaton condensate that becomes dark matter later on. And typically, say 98% of the initial energy goes to radiation through this process, and we are left with 2% of the remnant, and it behaves like the dark radiation for the moment because the potential is approximated by quartic potential. And only when the amplitude becomes very small, it fills mass and becomes dark matter. And at the same time, these actionic particles are thermalized in the plasma, and that would contribute to dark radiation or hot dark matter. So there are a couple of constraints. So it contains a couple of the parameters over the unity, but even though we vary those parameters over the unity, we found that for successful reheating, we have to be above this orange line. So coupling to photons is bounded below for successful reheating. And because the remaining condensate, inflaton condensate, behaves like dark radiation for the moment, and later on, it starts to behave like dark matter. And so effectively, dark matter appears at a later time, and which suppresses the density perturbation at small scales. So in order to be consistent with the small scale structure data, there's lower bound on the ARP mass. It should be heavier than about 0.05 electron volt or so. And also, actually, particles are thermally produced in plasma. It behaves like hot dark matter. And so we can put an upper bound on the inflaton mass from the hot dark matter constraint. So we are left with in this tiny parameter space, and where do we get the correct abundance of CDM? Actually, it turned out in this parameter space, we can explain the dark matter abundance. So as you can see, this is quite non-trivial that we have such an parameter space satisfying all the constraints. So we call this non-trivial coincidence as ARP miracle. And interestingly, there's also a hint for excessive cooling of horizontal branch stars, which suggests that the coupling to actionic particle with coupling to photons in this range, which is also consistent with this ARP miracle region. Okay, so in the remaining time, I will talk about different topics. So let me go on to the fifth force experiment. So if the axion exists, because it's coupled to spin of fermions, it induces a new force, the spin-dependent fifth force. And so here we introduce coupling, shoulder scale coupling to fermions like this. And also, if CPs are broken, it can have this scalar coupling to fermions psi. And by exchange of axion, the new force appears between this psi1 and psi2. And depending on which interaction you use, so you get either monopole-dipole potential or dipole-dipole potential. Both are spin-dependent. And in the limit of the massless scalar field, you can clearly see the dipole structure here. And the sign of the potential is, of course, physical because it determines it is attractive or repulsive. So sign is, of course, physical, and if it exists, that's very important for claiming discovery. Is the sign correct? That's the question. And I calculated this potential first time by myself. I got minus sign, but many people say it should be plus. I checked the references, and then it turned out that most of theory paper and experimental paper and many review articles, even including particle data group, say that plus sign is correct. And I found only one paper, theory paper, which says minus sign should be correct. And I got minus sign, but I was not 100% sure that if my calculation was correct. But I came up with a brilliant idea to check the sign. I asked my graduate student to check the calculation. Then he got minus sign, right? And we wrote a paper on it. And after that, another paper appeared. They also confirmed our results. So even though many people said plus sign is correct, but actually minus sign is correct. So it's better to check the sign if possible. And as a byproduct, we found that this spin-spin interaction, dipole-dipole interaction, actually the sign of it changes depending on the spin of the mediating particle. So in the case of the axion exchange, I said this should be minus, but in the usual magnetic field spin-spin interaction, it should be plus. But actually, in the case of gravity exchange, it is minus. But because of this, I don't know, unfortunately, the mistake, probably this simple structure was not recognized so far. So in the case of photon exchange, this opposite sign is favored energetically, but in the case of axion and the gravity exchange, the same sign is energetically favored. So this, of course, similar pattern was known to the spin-dependent, spin-independent force, but the same pattern should hold for a spin-dependent force. And in the last 5 or 6 minutes, I mentioned this cosmological production of axion. So if axion exists in during inflation, it acquires quantum fluctuation over the hyperparameter exactly like the inflaton. And it means that the axion will start oscillate with a different amplitude depending on the position. And this fluctuation has nothing to do with the fluctuation of the inflaton. That's adiabatic perturbation, and it's nothing but fluctuation of cosmic time. So, and even if you could somehow adjust cosmic time from point to point, you cannot get rid of the fluctuation between dark matter and photon. And this adiabatic and curvature perturbation exhibit themselves in a quite different way in the CMB temperature anisotropies. And this is adiabatic perturbation, and this is curvature perturbation due to the baryonic acoustic oscillations. If you neglect the cosmic expansion, this baryonic acoustic oscillation is nothing but the simple harmonic oscillator. And everybody knows the solution is just, you have two solutions, cosine omega t and sine omega t. And the cosine omega t corresponds to adiabatic perturbation, and sine omega t corresponds to curvature perturbation. And because of a different phase in the structure of those peaks, you can distinguish these two different density perturbations, and you can constrain on the amount of curvature perturbation. And so far, the size of perturbation should be about less than 0.4, so 4% of the adiabatic perturbation. And we can translate this upper bound on ice curvature perturbation into the upper bound on hyperparameter during inflation for given axial mass of axial abundance. And this is the result. X-axis axial decay constant FA, and the y-axis are hyperparameter during inflation, ranging from MeV up to 10 to the 9th GeV over here. So if the axion explains observed dark matter density, hyperparameter should be below this green curve. Okay? And for FA around 10 to 11th or 10 to 13th GeV, hyperparameter should be less than about 10 to 7th, 10 to 8th GeV, which is very strict constraint. And in particular, it is not consistent with the high-scale inflation, not only model, and only some class of low-scale inflation, like new inflation model, is consistent with this upper bound. So there are a couple of solutions to this axiom, a couple of ways to avoid the axial ice curvature constraint. The simplest one is to assume the pitch equisymmetry was restored during inflation or sometime after inflation. Then there's no axion during inflation, so there's no ice curvature perturbation. But in this case, as the axion appears when the UR peak symmetry gets pointed broken after inflation, which leads to the formation of topological defects, the cosmic string and the cosmic the domain walls at the time QC phase transition. And the annihilation of those topological defects lead to the copiously produced many axions, and the FA must be around 10 to 10th GeV in order not exceed the observed dark matter abundance. There are many other crazy ideas to avoid the ice curvature constraint. For instance, if the pitch equisymmetry was expressed broken by a large amount in the other universe, you can make the axion very heavy, then the quantum fluctuation gets suppressed at long wavelengths. Or one possible way is to consider the so-called Witten effect of the hidden monopoles. If there are hidden monopoles, and if axion is coupled to hidden U1 against symmetry, then axion gets heavy due to the Witten effect of the hidden monopoles, and you can suppress the ice curvature perturbation. And actually, in this case, you can also suppress the axion abundance. And depending on the parameter space, the hidden monopoles can be the dominant component. That if the axion really constitutes the main component of dark matter, and if it is found, it will have a significant impact on the early universe. So let me wrap up my talk. The axion is certainly a plausible candidate for physics beyond the standard model. And so, and I mentioned a crazy idea that the ALP accelerated particle may unify both infraton and the dark matter, and requiring successive inflation and also a couple of the dark matter abundance. So we led to this particular parameter space. Mass is about the 0.01 electron volt. Coupling to photons is just below the current the bound. So it will be checked by these future experiments. And yes, and there are many ongoing planned axion search experiments. Okay, that's it. Thank you very much for your attention.